So here we're going to talk more about polynomial equations. We're going to learn something very interesting and useful known as synthetic division. So we've already kind of spoken of this earlier. We have a polynomial function of degree n, meaning the highest exponent is n. And we know that there's some value x equals a, where when we plug in the value a into the function, we get 0. And a is some real number. Then we know from the previous discussion that x minus a must be a factor of this polynomial. Now we haven't focused on this so much, but we've started to mention it. Now let's really start to focus on this. If you have a solution x equals a, if you subtracted a from both sides, you would have x minus a equals 0. And kind of backtracking from that, that's the same thing as saying we have a factor of x minus a. Because if you thought about the zero product property, then you would set x minus a to equal 0. And what would follow from that is that x equals a is our solution. So we're breaking down p of x. If we have a 0 or a solution, we have a factor of x minus a with some leftover quotient that's 1 degree less. So that's going to be a fundamental idea that we're going to look into. So we have a higher degree polynomial, and they don't fit any of the forms that we've discussed in terms of factoring. What we're going to do is we're going to do synthetic division to kind of break down p of x of degree n into some 0, as written as a factor, times some quotient that is 1 degree less than p of x. Once we know what q of x is, then we could break that down and keep on going and going until we decrease the degree of the leftover polynomial to find as many possible solutions, or the remaining solutions. So here we have a function p of x. I'm going to rewrite it in kind of a weird way. We have x to the 4th, then we don't have any x to the 3rd terms, we don't have any x to the 2nd terms, we have an x to the 1st term, and then we have our constant term. So here's p of x, and I decided to write it out longhand as a polynomial to show every single degree starting at x to the 4th and decreasing by 1 each time. Now you'll start to see what we can do to kind of break down this 4th degree polynomial using the factor idea of the previous slide. So by inspection, when x equals 1, we know that we have a 0. That means that x minus 1 is a factor. That link is huge. If we have x equals 1 as a solution, so that means p of 1 equals 0, that's the equivalent statement of saying x minus 1 equals 0 is a factor of the polynomial. So now this looks weird, but we'll show you how it all works. Let's look at the coefficients of our polynomial here. The coefficient in front of x to the 4th is 1. Coefficient of x to the 3rd is 0 because there wasn't any x to the 3rds. Again, we have 0 for x squared, negative 2 in front of the x or the linear term, and then a positive 1. See how those numbers are listed in order 1, 0, 0, negative 2, 1. Those coefficients of the polynomial are listed out. Now don't forget you need those placeholders for the cubic and the quadratic term. You need those placeholders of 0. Now why do we put a 1 here? Because the 0 that we had, or the solution that we had, was x equals 1. So we put that over here, list out the coefficients, and then we're going to draw a line. This line's really, really helpful. It's like a good dividing line, pun intended. So now what we're going to do is we're going to take our polynomial and divide it by the factor that's given here. This is represented by this, meaning x to the 4th minus 2x plus 1 is 1x to the 4th, 0x cubed, 0x squared, minus 2x plus 1. And then dividing by x minus 1 means dividing by the 0 of 1. Notice how those signs are switched because this is a factor and this is a 0. Make sure you put the 0 up here, kind of by itself. So now what you do with synthetic division every single time is you multiply and you add. So if we bring down 1, that's what you're always going to do first. You have to remember to bring down. And then the fundamental maneuvers are going to be multiplying and adding. So you always start by bringing down, which is kind of the direct opposite of when you do division, but it's not the synthetic division. You usually bring down last, but we're going to bring down first. So bring down first, and I think of this region down here as the multiplication row. So now we bring down our 1, and then we're going to say, well, what's 1 times 1? That's our multiply action. That makes 1. We'll write it here. Then we're going to add vertically. What's 0 plus 1? That makes 1. So you see how we multiplied and then added. So 0 and 1 makes 1. Now since we're down here, I like to think of this as the multiplication row. We'll take the 1, we'll multiply it by the 0. That makes a 1. Add vertically is 1. We're in the multiplication row. 1 times 1 is 1. Add vertically makes negative 1 in the multiplication row, so we'll multiply negative 1 by 1. Negative 1 by 1 makes negative 1. We add, and we end up with 0. Now that's a really good thing. You need a 0 at the end in order for you to know or verify that x equals 1 is in fact a solution or a 0. If you were to do all this hard work out and get a number here that was non-zero, either one of two things happened. Either you found something that you thought was a 0, but it isn't a 0, or you made some mistake in terms of your bringing down, multiplying, adding. Through the process of synthetic division, you might have made a mistake. So it's either this is not a correct 0, or you made a mistake somewhere along the way. But if we know that this is a correct 0, and we end up with 0 at the end, or this is a correct solution, and we end up with 0 at the end, then we know that we've done the entire process correct, and there's no remainder, and we are dividing everything in evenly and cleanly. So now you have all these weird numbers, coefficients, and you might say, well, what the heck do they mean? Well, this is known, among other things, as the depressed polynomial. Now, it's a depressed polynomial because our original polynomial was in x to the 4th, or a quartic polynomial. The depressed polynomial is depressed because its degree is 1 less. We have negative 1, that's the constant term, go up a degree, 1x to the 1st, 1x to the 2nd, and 1x to the 3rd. See how this degree is 1 less than the original problem? That will always happen in synthetic division. So now we have broken down the original problem into the factor that we used originally, written as a 0, multiplied by this leftover portion from our synthetic division. Now, we could try to factor this further, but it doesn't look like it factors very nicely or neatly. But maybe what we could do is we could find, maybe we could use our calculator or something to find another solution here and then break it down. And we could do synthetic division then on this portion right here. We would list our coefficients of 1, 1, 1, negative 1. We'd find a 0 or solution. It might be 1, but it will probably be something different. And then we could break it down further and further, finding zeros and multiplying and adding after bringing down to do the synthetic division process to break things down further. So here's another example. Here we have this polynomial equation, negative x to the 3rd plus x squared plus x minus 1 equals 0. Now, one solution that we could directly observe is if we plug in negative 1, we're going to end up with 0. So let's try and see, now that we know that 1, 0, or that one solution, can we break down the polynomial to figure out more solutions? maybe more x values that are in here, let's say. So we take our 0, we'll write it right here. We list out the coefficients of the original function, -1, 1, 1, and -1. And then don't forget, you were going to basically multiply and then add. But don't forget the first thing you do is you bring down. Now we're here in this multiplication row, so we multiply and get 1, and add, get 2. Multiply, get -2, add, get -1. Multiply, get 1, add, get 0. Now we need a 0 at the end because we knew x equaled -1 was a solution, so there should be no remainder at the end. That number at the end should be a 0, or else we made a mistake. So now we can rewrite this original equation, but we broke down our cubic into this depressed polynomial, which is -1, 2, x to the first, -1x squared. Remember, it's a depressed polynomial because it is 1 degree less than the original polynomial that we were dealing with. So we can also factor out a -1 from this, which would change the signs everywhere. And then we could factor this a little bit more and break things down completely. Notice that we have a couple of x minus 1 factors multiplied together. That means x minus 1 squared. And then we can break things down further. And some interesting vocabulary springs up here. You look at this statement right here. You could use the zero product ruler property, and you could set x plus 1 equal to 0. That would give you a solution that x equals -1. And then right here, you set x minus 1 equal to 0. You'll get x equals 1. However, what's interesting is, see how this factor happens twice, because it was x minus 1 times exactly itself? We say that that 0 of x equals 1 has a multiplicity of 2, because it appears twice. See how it was twice? Now we could write it as it happening once, but we have the multiplicity of the exponent there, because that 0 happens 2 times. It appears twice. Okay? So now let's start to look at this in a different way. Let's consider the graph now of the previous example. We originally said that there was a 0 or a solution at x equals -1. And we just did this by inspection. But you could use your calculator if you needed to kind of grab a 0 from the function. You could just do a little, make y2 be 0, and then do second calc intersect where this is your y1, let's say. But so we had our 0 at -1, and then when we factored everything completely, remember how we said there was a multiplicity at x equals 1? A multiplicity of 2? So notice how it seems as if the graph kind of bounces or just touches the x-axis at x equals 1. That's no surprise, because when we had our multiplicity of 2, which is an even number, we just touch the x-axis. We just kind of bounce, or since we had negative values, we touch the x-axis and we stay negative. Why? Because we had an even multiplicity. We don't cross the x-axis. Here we had an odd multiplicity because x equaled -1 only happened once in the previous equation once we factored it. So you see how we cross on odd multiplicity. I like to think of the O and cross for odd. And then we kind of bounce for even multiplicity. Now, bounce is not a very technical term. We just touch the x-axis. We're not allowed to cross or cut through it. So that's an important concept to kind of notice. and take advantage of. And it's really good to think not only in terms of equations, but also in terms of graphs. So this graph does correspond to this equation, which was factored in the previous example or slide. But it's very good to see how everything relates, how the graph tells a story, and so does the equation. It tells the same story, and kind of have both sides to that coin in your mind. Here we're going to learn about the rational roots or rational solutions test. Now we're going to focus on the constant term and all of its factors. That's known as P down here. And the leading coefficient and all of its factors. We're going to make a ratio of P to Q. And bear in mind that we're looking at the ratio of all of the possible factors of P divided by all of the possible factors of Q. So there's actually many possibilities, but this is a nice way to kind of look at good possible candidates, rational candidates that could be roots or zeros of this polynomial equation. So the rational solutions test or rational roots test provides a list of possible rational roots or zeros or solutions. Now it's just the possible ones. Every single rational possibility is only a possibility. Only some of them may actually be actual solutions or zeros. So there might be no rational factors. You could probably manufacture a polynomial in 3 seconds that has no rational factors. Maybe take some irrational factors and kind of manufacture that polynomial. So let's look at this specific example to help make sense of this. Notice how the coefficient of the lead term is 1. That's like our Q. And the coefficient of our constant term is 18. So now we're going to look at all of the possible factors of 18. Well, 18 could be a multiple of 1, 2, 3, 6, 9, or 18. So all those factors could be in the numerator. And you can actually write it like this. You could say, like, oh, I'd have plus or minus 1 times plus or minus 18. I could have plus or minus 2 times plus or minus 9. I could have plus or minus 3 times plus or minus 6. Now those are all of the possible factors of P. Now keep in mind I use plus or minus. Now those factors could be over plus or minus 1 because Q, the lead coefficient, only has factors of either 1 or negative 1. So then you look at plus or minus 1 over plus or minus 1 and you get plus or minus 1. Plus or minus 2 over plus or minus 1, you get plus or minus 2. And so on and so forth. These are all of the possible rational solutions. Now these don't have to be guaranteed to be rational solutions or rational zeros of this polynomial equation, but those are all the possible rational candidates. So they're all the ones to try and do what on? Do synthetic division, which is what we just learned before that. So now you can start to begin to solve cubic and quartic equations when you have some polynomial set equal to 0. So we can determine all the possible rational solutions using the rational roots theorem, which states that we are going to look at all of the possible factors of the constant term divided by all of the possible factors of the coefficient of the leading term. So we could graph using our calculator to find a 0 or an x-intercept. Once we find a rational solution, hopefully it's an integer. Once we have a 0, let's say, from the graph. Then we'll have a factor, x minus a. Once we have that factor, then we can use synthetic division to break down the polynomial equation to 1 degree less, and then we can keep breaking things down further and further to find more and more solutions, or zeros, or x-intercepts. And we will discuss this more in the future, I assure you. So this fundamental theorem of algebra is quite helpful. What I'd like to do is I'd like to really just focus on this key idea right here. If we start to think about imaginary or complex solutions, well, the fundamental theorem of algebra says if you have a polynomial of degree n, like let's say n was 7, you're going to have exactly 7 zeros when you break down this 7th degree polynomial. Now, you have to keep in mind, we can allow for some imaginary or complex zeros in there, and then we can allow for some real zeros to be in there. Now, the important thing is that if you have one imaginary zero, you're actually going to have the conjugate pair of that imaginary zero. So complex or imaginary zeros always come in pairs. For instance, if you have a zero or solution of 2 minus 3i, you will have 2 plus 3i as well. So it's kind of an interesting feature, and we can discuss the nitty-gritty details of this a little bit more in class. I can give you some examples on this because it's kind of a beautiful, interesting theorem that it's going to take a little bit of discussion. But basically just know that if you have an n-degree polynomial, it can be made up of n solutions, or zeros. Now, those n solutions can be a mixture of real and imaginary solutions. But if you have one real solution, you aren't guaranteed necessarily another real solution. But if you have one imaginary solution, you will also have its conjugate pair. So imaginary solutions always come in groups of 2 or in pairs. And we can discuss this more in class, and I look forward to it. So here's another example where we factor by using a greatest common factor. We use the zero product property or rule to set t to be 0 and t squared minus 2t plus 3 to be 0. Then we can do the quadratic formula on this. If we clean up the square root of negative 8 and simplify fully, we can have our conjugate pair. So we have two solutions, 1 plus I root 2 and 1 minus I root 2. And then we also have t equals 0 because don't forget that greatest common factor could be 0. So this is just illustrating the fundamental theorem of algebra a little bit, and we will discuss this more in due time.